Hey, what's up? Today I'm going to try to explain to you guys the concept of what these things are. What are these calculus notation things? Because I don't think people or teachers cover these very well in class. So what does dy mean, and what does dx mean, and why are you free to manipulate these however you want, and what do they stand for in context, other than just notation? So let's start off with what dy over dx is. This is the derivative, as you guys might know. And the derivative is a better way of just saying like slope at a certain point. And the average slope at a point is just change in y over change in x. This is probably a review for you guys. But the formal definition of a derivative is the limit as c approaches a, and then f of c minus f of a over c minus a. And that's how you calculate the derivative. And using limit laws, you can split this up into two limits, individual limits. Limit c approaches a, f of c minus f of a. That's your first limit that you got from up here. You can use limit laws. And then your second limit, limit of c approaching a of, this thing, c minus a, so, and this is all going to be equal to your derivative. So in the end, you get this. Oh, and by the way, over here, c and a are just like some arbitrary points. So like on a function, a comma b is the point at which we want to find the instantaneous slope, and c comma d is like it's like a dummy point that we want to use to manipulate these to find the slope at the point. We would actually care about what c comma d is because it's never like a singular point. So yeah, it's never actually defined. So you get this and you get that. So let me just explain this real quick. So you get the limit as c approaches a, f of c minus f of a, and that's going to be equal to dy, okay? So try to make sense of that. It's basically 2 points on the function getting closer and closer to each other, and over here so they're getting closer and closer to each other, but over here you're only kind of thinking of it in respect to, with regard to the y-axis, and the same thing's happening on the bottom over here. C approaches a, and so the 2 points are getting closer and closer to each other. So, but you're only kind of considering it on the x-axis, so this is just dx. Okay, if you want to think of this in a better way, you can kind of think of d as like distance. Okay, so the distance between the 2 points in terms of y, and the distance in 2 points between in terms of x, and this distance is getting infinitesimally small, as we said through our limit statement and by the definition of derivatives. So that's basically like a quick overview of what these two things are. But other than just derivatives, so you can also, does it also make sense? Because you can think of it like, you can think of it as the change in y over the change in x, as change in y and change in x are getting infinitesimally smaller, if that makes sense. So now I'm going to move on to integrals and just say a bit about it, although like I think this should be pretty easy to figure out. So integrals, say this is f of x, the motive of an integral is to find the area between two certain points on a curve. So I just said this is our first point and this is our second point, and we want to find all of this area in between. This is what we want to find, and that's what the integral finds for us. So what does this dx actually do? So for that, I'm going to start off by kind of reminding you guys what an integral actually is. So let me explain this to you guys. An integral is basically when you kind of sum up the rectangles between a curve, underneath the curve, and basically what I mean by summing them up is you kind of split up the curve into d-sized portions. So like let's say the length of the rectangle is d, and then the height is some point on the curve. And using this, you get a pretty good, if you like keep on making rectangles here, like you make another rectangle here, and so on and so forth, and you cover the entire thing, you're gonna end up getting a pretty good approximation of what your of what the area under the curve is. So basically, you've got a rectangle of length d and height f of f of x, but in this case x is just 0 because it's starting from 0. So to put it more formally, you got f of x plus f of x plus d plus f of x plus 2d, and so on and so forth, because these are all your heights, okay? And then you multiply it by the length. which is d. So this is the length. Sorry, and this is the height. Okay, these are the heights. So now, because if you can look over here, you're missing all of this nice stuff for the area. So that means you're actually underestimating the area. You're like getting a bad approximation of what it is. It's like a good starting point, but it's not what we want. We want like pretty much exact answer. So what you're gonna end up noticing is that, hey, maybe if you make these rectangles widths infinitesimally small, then maybe we'll get a better approximation. Maybe maybe the amount that we're missing is negligible at that point. So if you do that, then you get exactly what we did up here. You make the difference in x infinitesimally small. So you look at the difference in x when it's getting infinitesimally small, and that's your length. And then the height is just all of these. So the way I like to think of this is you're multiplying the all of the lengths, so that's dx times this thing, and I think of this thing as being this thing, except you kind of also think of it in terms of limits and the way that we thought about it for d of x with infinitesimally small intervals. So d would be like very 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 small, and so you just kind of sum up all of the points on the curve, all of the y values on the curve, if that makes sense. So it's basically all of the sum of all of the heights times all of the lengths, and that's going to be the area under your curve. I hope this helps. Thank you.